So, good morning to all. Good evening to Volker. Dear colleagues, let's start. Today is open lecture at Kharkiv National University of Radio Electronics. We have here special guest. Let me introduce Mr. Volker Rademacher. He is an expert in area of embedded systems and lives and works in North American industry for many years. It includes projects of different complexity, and Mr. Rademacher actively participates in activities of our department and supports us in different ways. The goal for today is to provide you with insight into a topic of controller external devices that will be a partial subject of your study for next semesters. And please, Mr. Rademacher, you may start the lecture if nobody wants to add something. Okay, welcome.
Would it be possible that you show the slides and I make comments from here?
Олексій Миколайович, можна презентацію?
Так, зараз.
Thank you.
Бачите презентацію? Все добре?
Yeah, we see the presentation. Thank you. Volker, do you see the presentation?
Sorry?
Do you see the presentation?
Yes.
Okay, thank you.
Okay, thank you so much. Okay, next slide, please. The reason why I'm asking is I've noticed that just right now there have been some changes made, some updates made, and I'm not entirely sure. I didn't have the time to download the latest version. Okay. Yes, this lecture is intended for power control circuits, components. The time is not really enough to go into full detail for everything, but I'm hoping to raise some interest so that the students can, on their own, also research some topics that I'm focusing on, that I'm starting here. Next slide, please. Okay. So microcontrollers are the core of most embedded systems. I have here in those images just some of the items that are usually of interest. So I have three different types of motors displayed: a three-phase motor, a brushless DC motor, a stepper motor. I have some less complicated loads, for example, the heater, the red device. There is a solenoid valve. Then there is some fairly popular RGB lighting with the WS2812 circuit, which is also very popular to control with microcontrollers. Okay, next slide, please. Okay, software that is running on a microcontroller is called firmware. Microcontroller firmware can read, set, and clear port pins on a microcontroller component. That is really at the core. I have some examples here of some codes that I grabbed from projects that I was working on. In one case, I was reading push button inputs. In the hardware, these were push button inputs to ground, which is very common, and I will be explaining a little bit of that later as well. And you can see in the first example where it says read the state of the digital inputs, that I'm using the ternary operator, that is a question mark, to generate Boolean output. I'm using HAL functions, that is the hardware abstraction layer, for the STM32 microcontroller development environment. So it makes it fairly easy to use commands to read pins, to write pins, to set up microcontroller peripherals. But the problem with the HAL functions is that it uses a number of its own data types. And in this case, I was using the ternary operator to generate like a purely Boolean data type. And in addition to that, I'm also inverting the result because the actual push button, the actual switch is switching to ground. So low is the active state here. The second example is an example where I'm writing a pin. I'm again using the HAL functions, the hardware abstraction layer functions, where I am writing to an LED output. And I'm starting the timer peripheral to prepare for starting of a PWM output. PWM is pulse width modulation. It is usually being used for motor control in some form. However, in the third example underneath, where I'm actually setting, that's a macro that is actually setting the duty cycle of the PWM. In this case, you couldn't tell from the command, but you can tell from the comment. It is actually intended to set the output of an RC servo, the remote control servo. And remote control servos use PWM, but not directly for motor control. It is, in that case, more of a communication method. Basically, the pulse width directly corresponds to an angle on the remote control servo. And if that is of interest to students, then I can absolutely present further examples in a separate presentation, or I can just provide some sample code to your professors. A microcontroller is based on digital logic and is designed to interface with industry standard digital logic. I'm writing that because if you are just writing code and you're not quite entirely sure what does it interface to, what does the outside world look like. So I want to explain a little bit, and I have to talk a little bit about the history of industry standard digital logic. Okay, next slide, please. Okay, I am holding this presentation for the Department of Electronic Computers. And some students might be asking, are there any other computers? Aren't all computers electronic computers? But I just want to point out that before digital electronic computers, there used to be analog mechanical computers. Those were not like computers today. They were mostly used by the military. They were primarily used as, for example, fire control computers. They were large devices, but in the 1930s, 1940s, pretty much every large ship had a mechanical computer that was acting as a fire control computer. They were heavy. A US destroyer in 1943 or so had a fire control computer, mechanical, that weighed 3.5 tons. However, it was possible in those days it was sufficiently accurate to shoot down airplanes, which is pretty impressive. After mechanical computers, there were electronic and digital computers. that I haven't mentioned here. There were electromechanical computers. Then the first electronic digital computers. Those were powered by vacuum tubes. And that doesn't really affect us much. However, the first solid-state electronic computers used individual transistors after the transistor was invented. And again, mostly driven by the military, they wanted more faster computer systems to, for example, trace radar distribution, antenna. They wanted to simulate tasks. There was a lot of money behind it, and so the development never stopped. On the upper and the right-hand side top, you can see what, for example, like a circuit board that is the equivalent of a digital logic gate. Sorry?
Mm-hmm.
No, it's background voice, sorry.
Was there a question? I'm happy to answer questions.
No, it wasn't question, Volker.
Okay.
Please continue.
Okay. So that was in the 1950s, 1960s. That was when the development, when people started knowing what they wanted. Semiconductors became cheaper, transistors became cheaper, diodes became cheaper. They designed logic families that are completely not in use anymore, that were never really integrated. RTL logic, DTL logic. However, all the concepts of digital logic were pioneered in those days. And when digital logics integrated digital logic circuits entered the market, that was around 1963. The designers knew pretty much what they wanted and what they had. And I'm saying this, I'm going this far back into history because we are still seeing the results of these design concepts on the next few slides. And that continues on into the microcontrollers that we want to talk about. The first popular integrated circuit logic family was the TTL and the CMOS family. Probably everybody has heard of the TTL 74, the 7400, and there's a whole range of integrated circuits that exist from the TTL family. The CD, the Motorola CMOS-based family does not exist in that form anymore. However, a lot of the integrated circuits from that family have been transferred into the 7400 family. And I will be talking about that as well. One quick comment about when the digital logic was pioneered. In the lower left-hand corner, there's a little diagram. That diagram is a KV diagram. It's a Carnot-Veitch diagram. That is how initially logic gates were being not calculated, how entire logic circuits were being calculated. I don't know if that is still being taught at universities in Ukraine. I know I've asked some of my coworkers, and when they went to school, yes, it was still being taught in the digital logic courses. Um, in those days, people designed a truth table of the inputs and outputs that they wanted, and they wrote the inputs and they wrote that up and entered that into one of these tables that you can see on the lower left-hand corner. And then they designed a Boolean equation from that table. They optimized it, designed a Boolean equation from that table, inverted it again, used the De Morgan rules, and the logic circuits that you wanted could be mostly implemented in NAND technology, not AND, and inverters. That is one of the reasons why, and now I'm flipping over to the next slide. Next slide, please. Oh, okay, yeah. That is one of the reasons why when the TTL family was designed, a lot of NAND logic gates, not AND, and inverters were basically the first pieces of that family. The 7400 chip that you can see here in one of the pictures is for 2-input NAND gates. There are 3-input NAND gates. There are 4-input NAND gates. There is a 13-input NAND gate somewhere in that family. There are inverters. There are NAND gates with Schmidt trigger inputs. There are NAND gates with open collector outputs, which we're going to talk about. So if you're ever looking at that entire family of logic chips, there are more NAND chips than AND chips or OR chips. And that is the reason why, because the way how digital logic was designed and optimized in those days favored NAND technology. Also, from that time, the chips that you're seeing there, the pin layout, pretty much exists to this day. The TTL family was followed up by more modern logic families, more modern technologies, but the core functionality and the pin layouts stay the same. For example, in this image, you can see the chip in a DIP layout, dual inline. And you can buy the same chip in a newer family, in an HCT family, and the chip will still have the same pinout, even though it might be in a much smaller package. It might be in a SOIC package or in an SSOP package or in a DSSOP package. It will still have the same pinout. So that was pioneered in the 1960s, and we are still living with that today, basically. You can still go to the store and buy a follow-on, like a newer chip with better technology. It has the same pin layout. I'm continuing here. TTL logic was fast and rugged. CMOS logic had a wide voltage range and was extremely low power, sensitive to ESD. The old CMOS logic was very low power even today. Even for today's power ideas, it was a very low power technology, but the original CMOS logic was not fast at all. So in those days, the idea for these logic chips was not for them to be supporting a microprocessor. They were not meant to support a microcontroller or microprocessor. They didn't exist. The idea was for these chips to be a central processing unit, to build a central processing unit from hundreds and hundreds of these chips. That is the reason why you can still see, if you look at the family members of the TTL family, you will see a lot of integrated circuits, a lot of chips that don't seem to serve any purpose anymore, that are still available for purchase, but who needs 4 different versions of 2-input NAND chips? Who needs several types of 4-input NAND chips? The reason why these existed was because they were not intended to be support chips. They were the components, the building blocks of actual computers. And again, I'm just saying this for a general understanding of where we are coming from, where the technology in microcontrollers and in logic chips comes from. The original TTL family is obsolete. I had mentioned that the high-speed CMOS TTL and the low-voltage CMOS series are the most popular at the moment. They are newer families. They might take over at some point in time, But at the moment, if you're looking for a TTL compatible circuit for whatever reason, that is supposed to be connected to a microcontroller, you most likely will be choosing a high-speed CMOS chip or an LDC chip. I think I'd mentioned that before. The Motorola 4000 line doesn't really exist in that form anymore, but a number of circuits or integrated circuits from that line were unique enough that they were integrated into the TTL compatible line. And you can usually tell because after the 74HC, they have 4 digits afterwards. That is right away an indicator that this is a chip that is compatible with one of the early CD4000 digital logic chips. Okay, next slide, please. The original TTL technology required a supply voltage of 5 volt and the used voltage thresholds of 0.8, 2, 2.0 and 2.4 volts. You can see in the upper right-hand corner that image with those different bars, the vertical bars. You can see there that the 5 volt TTL line has a significant noise immunity that they tried building into the digital logic. The way how these logic thresholds should be interpreted is actually the 0.4, 0.8, that is not quite the TTL. But so the lowest value is for the low state is the value that a gate output cannot be higher. The next value is the output that a gate input must detect a low state. So there's usually a 0.4 volts of noise immunity in between. For the high value, a logic input is supposed to register any value over 2 volts as a high, and the logic output has to supply at least 2.4 volts. In general, an old-style TTL circuit that was supplied with 5 volts was capable of outputting around 3.5 to 3.6 volts. The reason why it couldn't output 5 volts is visible in the other picture. There's a resistor in above Q4 and a diode, and those have voltage drops. And here's now something important. When these chips were designed, someone decided that a standard gate should be capable of driving 10 inputs. In those days, one input was actually consuming power. It's not unlike it's not like the CMOS inputs that we have nowadays that essentially are high impedance. Driving an input low consumed power. And the chip was designed to drive up to 10 inputs. The usual logic gates, standard logic gates, were designed to drive up to 10 inputs. Why 10? I don't know. But one input consumed about 1.6 milliamps. So, and this is basically continuing through this current value, this current capability is essentially continuing through the decades until today. So in effect, the whole TTL output was capable of supplying 16 milliamps while maintaining logic levels. So all follow-up logic families are roughly around that value, plus minus 50%. So you have, for example, HCMOS logic. They are intended for 8 milliamps of maximum output while maintaining voltage levels. The LVC family can output 24 milliamps while maintaining voltage levels. I'm emphasizing here voltage or current output while maintaining voltage levels, because you can pull out more current out of the outputs. But then the TTL or the logic output levels aren't guaranteed. And of course, at some point in time, one would have to make sure that the maximum allowable values aren't exceeded. So this decision to drive 10 outputs basically is following us up until now, where newer logic families, microcontroller outputs will always be around that value of output current capability. Some more, some less, but it is usually somewhere between 10 and 25 milliamps. It would be very unusual for a microcontroller to supply more than 25 milliamps. And in any case, if you're using a microcontroller, you should not be maximizing the output current out of a microcontroller pin, because it might affect other peripherals on that microcontroller, in particular the analog to digital converter. I'm just continuing. Modern HCMOS logic will work across the supply voltage range. I'm emphasizing that here because the original TTL chips were limited to 5 volts. HCMOS logic, high-speed CMOS logic, doesn't really care. They will take anything between 2 to 6 volts. They can work at 3.3 volts, which is another common voltage. And so the logic thresholds aren't as defined anymore as they used to be for the TTL family. So in general, the detection, the input thresholds are set at 30% and 70% of supply voltage, whatever the supply voltage may be. The output voltage is rail to rail, meaning supply rail in high state and ground in low state, because they use MOSFETs for the output stage, and they do not require the extra resistor and diode to avoid. Really, it's to avoid having the transistors go into saturation. It's also there to avoid current, shoot-through current for a brief moment when both transistors are conducting in the gate, inside the gate. So 5 volt supply voltage is still in use. It's also still in use for microcontrollers. The popular Arduino series of development boards, they use an Atmel ADR microcontroller, and that is a 5 volt type, for example. A lot of the microchip PIC microcontrollers are still perfectly usable for 5 volt operation, but most professional commercial digital logic uses 3.3 volts, and pretty much all STM32 devices are 3.3 volt devices. Modern logic families provide typical output currents of 8 to 24 milliamps while maintaining logic voltage levels. I mentioned why when I started this. There might be a little bit less, there might be a little bit more, but generally it is around that value. There is no normal logic output on microcontrollers or digital logic that is using much more than that. You won't find anything that outputs 200 milliamps. That would be a driver chip. That would be separate from digital logic. Okay, next slide, please. A few words about the circuit design, because from that original TTL logic, a number of concepts, a number of circuit concepts came to be that are still being used. So the original 5 volt TTL family reads an open input as a 1, as you can see from the internal gate description in one of the images, actually in 2 of the images. The original TTL family use emitters as inputs. The active state was 0. If they were just left open, they would be read as a 1. This circuit principle or the use of emitters as inputs, was basically being abandoned with the next iteration of the family. That was the LS, the low power Schottky family. But the idea remains the same, that most of the circuitry evolved around using the active state, using an active state that is actually a low state and not a high state. So you see in the image in the upper left corner, the gate internals, that is an open collector output. That output is only capable of pulling a signal low to ground and not up. And these usually were used with pull-up resistors. And this principle is still around today, that a lot of logic that we're using is actually negative logic, where the active state is ground, the active state is 0. In the context of microcontrollers, a lot of microcontrollers will allow for a GPIO port to be configured with a pull-up resistor. Not as many allow for a pull-down resistance ability. It is just not common. The STM32 series does have that capability, but for example, the Atmel AVR family does not. The Atmel AVR family does allow for a GPIO input to be configured with a pull-up resistor, but not a pull-down resistor. For today's CMOS gates, the difference is that the gate is high impedance, or the gate input is high impedance and cannot be left floating. In the old TTL technology, a gate input could have been left floating and it would be detected as a high. The newer technology logic gates cannot be left floating, because in that case, it would just simply generate oscillations. It would pick up noise from surrounding EMI. So those gates require a dedicated pull-up or pull-down resistor. And while a pull-down resistor didn't make much sense for the TTL family, for a CMOS gate, for a CMOS input, and that includes the logic gates and the microcontrollers, a pull-down resistor is just as good as a pull-up resistor. The gate input doesn't care for the CMOS gates, which is pretty much everything nowadays. There is one important other item that I wanted to mention. In the CMOS logic versus TTL logic display, there is an image shown. Sorry. There is an image shown where there are where you can see MOSFETs replacing the transistors. MOSFETs have a built-in internal body diode, which is not shown in that image. So you have to imagine that every output, and actually most inputs as well, have two diodes from the output, directed to the supply voltage, and from ground directed to the output. These diodes are not shown, but they're important when you get to high side drivers, because those protection diodes prohibit certain configurations if you're trying to create a high side driver the same way that you're trying to create a low side driver. We'll get to that, hopefully. Yeah, so the concept basically that I wanted to mention is that open collector, open drain, which is essentially just a transistor or a MOSFET that can pull to ground without having the equivalent MOSFET or transistor that can pull to high, to VCC. The idea that there are pull-up resistors are much more common than pull-down resistors. And the third concept is the Schmidt trigger. As part of the development of the digital logic, a maximum rise and fall time was defined. For signals and the outputs of digital logic was guaranteed to stay within the limits of this rise and fall time. It had to be faster than roughly 40 to 50 nanoseconds to work properly. For signals that are slow, a solution had to be found, and that solution is called a Schmidt trigger. So a number of logic gates that you can find in the 7400 family, and that you can also find on some microcontrollers, have so-called Schmidt trigger inputs that provide what's called hysteresis. You've probably heard of Schmidt trigger inputs if you have worked with digital logic before. So a number of circuits that are already existing in the TTL family, NAND gates, inverters, are available with these Schmidt trigger inputs in the same package form, in the same pinout. For example, for the 7400 for NAND gate circuit, it is the 7432. For the 7404, which is 6 inverters, which is a very popular circuit, you have the 7414, which is the same package and is the same pinout. It's just all the inverters in that package have a Schmidt trigger input and can be used for slow changing signals. And that might be important, for example, if you're using a filter before a push button input, or if you're using a filter that is slowing down a signal to remove noise, and for an input signal. So the filter removes noise, but also makes the signal transition very slow. In that case, you have to use a digital gate with a Schmidt trigger input. Old microcontrollers, some 8051 derivatives, they're still around. 8051 still exist. And some ports in the 8051 microcontroller, there are no push-pull outputs on those ports. I think it is at least one port of the typical ports in the 8051. And they can only pull to ground with significant strength, and they have essentially weak pull-up resistors to pull the signal up to one state. That is, if you're using an 8051 for digital circuitry, that might be something to consider. Okay, next slide, please. Typical external loads. I just grabbed two images, a light bulb and a fan. The fan is an AC motor. The light bulb is basically a heater, like a standard old light bulb. It provides mostly heat and a little bit of light. These are just examples to indicate that we have loads that create motion, and we have other loads, in this case, for example, heating element, which is mostly resistive, but not necessarily linear. A light bulb, for example, will have a much lower resistance in cold state than it has in hot state, in on state. So the resistance itself is not linear, but it is a resistive load. Inductive loads, which are the vast majority of loads that are in any way connected to motors or anything that moves. Inductive loads have some very specific properties that need to be known before you can drive them with a microcontroller. Okay, next slide, please. Inductive loads, solenoid valves, relays. Solenoid valves are, or solenoids, are essentially just large coils, large inductors. They're intended to either, in the case of a relay, to basically attract a magnetic or a ferrous metal piece to change, to move around, to change position. The same with a simple solenoid, which is effectively a linear actuator, but it just relies on the magnetic field to pull in a piece of ferromagnetic material and create movement that way. So solenoids are purely inductive, and inductors are energy storage devices. The energy is stored in a magnetic field. The problem with inductors, with pure inductors, is that they are kind of opposite to capacitors. Capacitors try to maintain voltage and will try to maintain voltage at any cost. So, for example, if you have a capacitor charged up, it is sitting at the voltage that you have it charged up. If you short circuit a capacitor, it will attempt to create a current high enough to maintain that voltage, which means if you have an ideal capacitor and you have an ideal short circuit that has 0 ohms, then Ohm's law still applies and you will get an infinite current. And anybody who has used a large capacitor and has short-circuited a large capacitor knows that a large capacitor, if you put a screwdriver across the terminals, it can basically it can weld the screwdriver to the terminals, because for a very, very brief moment, the current can be really, really high. Inductors are like that, just with current. An inductor is attempting to maintain its current. If it's running at a steady state current, it is trying to maintain the current at any cost. So if you interrupt the current flow, Ohm's law still apply. The inductor will attempt to create a voltage as high as it needs to be to make that current continue flowing. So inductors can generate thousands of volts and break pretty much any electronic component if it is not taken into account that the energy stored in an inductor needs to be dissipated. For this purpose, relays usually have a flyback diode. And we are going, or other solenoids have a flyback diode. Here is another critical item that needs to be observed. It is very easy to think that a flyback diode around a relay, and we're going to talk about those in the next section that deals with relays. A flyback diode typically a normal silicon diode is being used. It has a voltage drop of 0.7 volts. Sometimes I see people thinking that they can discharge the inductor faster by using a Schottky diode, which has a voltage drop of 0.3 volts. However, that is not the case. It is very counterintuitive. The higher the voltage, the discharge voltage, the faster the inductor is discharged. If the diode had a voltage drop of 0, the current would never stop. That is very hard to understand, or to intuitively understand. I'm just mentioning it, that using a silicon diode as a flyback diode is perfectly fine. It does not need to be a Schottky diode. It just makes the discharge slower. Inductive loads can create very high voltages. I just explained why. Electric motors, however, are a different beast. Electric motors create motion through rotating magnetic fields. Brushed DC motors are internally commutated. I'm mentioning that because we possibly at some point also want to talk about brushless DC motors, where essentially the electronics has to replicate the features of the brushes, the internal commutation that is happening at brushed DC motors. Other electric motors require an externally generated rotating magnetic field. Most popular, of course, are, for example, three-phase motors, high-power three-phase motors, where essentially the power supply from the mains, like from the electricity provider, is by itself already presenting that rotating electric field. That is the easiest to implement. AC electric motors on startup can create very high inrush currents. That is another very important thing that needs to be considered. That is, if you have an electric motor that is standing still and you're trying to drive it with some kind of driving, low side, high side, bridge driving circuit, it can, the startup, the inrush current can break electronics and needs to be accounted for. Stepper motors are usually current controlled, can drop out of rotation. This is another type of motor that I wanted to talk about. So stepper motors have other features. You are creating, or the microcontroller is creating the rotating magnetic field. However, the purpose is different. And the purpose of the stepper motor, or one of the big features of the stepper motor, is that it provides torque even when it's standing still. An energized stepper motor does not need to rotate to have torque. Usually what happens is when it's standing still, then the windings, the winding current in the stepper motor coils is a winding current would be increasing to a point where the stepper motor burns out. And to avoid that, in most instances, a stepper motor is being current controlled through a chopper. The user effectively, or the circuit effectively, controls the amount of torque that the stepper motor has. The downside of that is that a stepper motor that is rotating will basically just abruptly stop if it's getting overloaded. When it is moving, when the stepper motor is being moved to a different rotation speed, there are instances where it can fall into mechanical resonance, and it will also just abruptly drop out of rotation. That's a different topic to discuss. Okay, next slide, please. Linear control versus switching. So we have discussed the loads a little bit. Now we want to control what do we do with these loads? We have discussed the current capability of a microcontroller, and I forgot to mention that the current capability of a microcontroller is way too low to directly do anything with one of the external devices that we're trying to control. 3.3 volts or 5 volts at 16 or 20 or even 25 milliamps is by far not enough power to do anything useful. It is enough to light up an LED. It is enough for a very small relay. It is enough for a buzzer if needs to be. But even then, in most cases, even a buzzer will be operated by an additional switching device, by an additional amplifying device. Why do we use switches, or why is our goal to switch components, external components, instead of providing, for example, a linear changeable voltage to these components, if we want to change the speed of a motor, for example. The reason for that is because we are trying to minimize the power loss in the controlling component. Power dissipation in the controlling component generates heat, requires heat sinking, reduces reliability and efficiency. Most importantly, the problem is the efficiency. And of course, that directly relates to heat. If there is a component that generates heat and requires heat sinking, the question is what to do with that heat. In many cases, you will need to, or the designer will need to install, for example, a fan. A fan makes it more difficult to waterproof a device if it needs to be waterproof, because the air has to be coming from somewhere. So the best solution is to avoid excess heat altogether. Linear control of a load is similar to using a resistor to adjust load power. And if you do that, then you're using the same power as before. You're just trying to burn off excess power in that resistor as waste heat. I have an example in the upper right-hand corner that is like a very coarse schematic of a linear power supply. In that case, the power transistor essentially is designed or is intended to waste the heat or to waste the energy that is being generated by the difference between the supply input and the intended supply output. Linear voltage regulators used to be very common because the implementation of switched voltage supplies was difficult. It is not difficult anymore. So nowadays, pretty much all power supplies are switched power supplies, simply because it is not efficient to waste heat and require a large area for heat dissipation or expensive heat sinks, or fans for that matter. Switching a load does not waste power, simply because an ideal switch either turns fully on or it turns fully off. If a switch is turned fully on, that means its resistance is zero. If its resistance is zero, then it doesn't matter how high the current is, the power is still zero. On the other hand, if the switch is fully off, then the current is zero. And again, in this case, it doesn't matter how high the voltage is. If the current is zero, then the dissipated power is zero. So an ideal switch that is either fully on or fully off does not consume or does not waste any power. Switch control can replicate the functionality of linear control if the load is an integrator. What do I mean with an integrator? Basically, an integrator can also be a filter. We are trying to very fast switch, for example, a supply voltage, so that little portions of that supply voltage can go into this integrator and come out as like one solid, as a steady state voltage that doesn't have any switch remnants anymore, any pulses anymore. And in the case of the switching power supply, the inductor and the follow-up capacitor in the image that I have on that slide is the integrator. It is a filter. It is an LC filter. And most loads that we're dealing with will be integrators, simply because, for example, an electric motor, if you're switching an electric motor with several kilohertz of frequency, the inductance of the electric motor and the mechanical slowness of the motor, of the mechanical parts of the rotation of the motor, will effectively integrate the switch, the high frequency power supplies, the power switching. So for most electric motors, it is possible to use a switched power supply, and this is called in most cases a PWM, a pulse width modulation. If the frequency is high enough, you won't notice at the motor that it is driven by a PWM frequency, by a PWM drive. If the PWM frequency is too slow, you might notice that the motor is jittering a little bit. So then you need to increase the PWM frequency. Integrators can be non-electrical, the thermal mass, or also, for example, if you are using an LED. In most cases, LEDs are not driven by PWM as well, and they are not voltage controlled. They are switch controlled. They are PWM controlled. And in this case, the integrator is the human eye. So the LED might be flashing at 1 kilohertz frequency, and with a PWM that makes the LED appear brighter or less bright. But because the human eye cannot follow the fast switching frequency and effectively integrates this, you can happily drive an LED with high frequency or with a relatively high frequency PWM, and it will look as if it is driven by a changing voltage or a changing current in this case. Okay, next slide, please. So we have just discussed that switching a load, switching a motor, switching any kind of inductive load, for example, or even a resistive load, switching a heater, for example, all of that is preferable to linear control. So we want to switch. So now I want to quickly point out what are the problems, or what do we need to consider when setting up a switching driver. In non-ideal switches, power is dissipated during the rise and fall time between fully on and fully off. There's a quick image on the right-hand side that indicates like a rise time, fall time. Shortening the rise and fall time, harder switching or hard switching, can increase the efficiency because less power is being wasted. So it increases the efficiency and it creates less heat. However, the drawback is that the harder you switch, the more electromagnetic interference you're going to get. That is, you can calculate this. This can be calculated by using the Fourier transform, the step responses, and it is just a trade-off between efficiency and EMI, electromagnetic interference compatibility. The other item is that hard power switching, because there are very, very high harmonics that are being generated, so hard power switching can create failures. I've seen it in one instance, for example, where a coworker was trying to design an inverter that inverts from 60 volts to 120 volts. And he was using a bus bar. And even though the bus bar was like a thick piece of solid copper, it had enough parasitic inductivity that the ring was created, that there were enough overvoltages through the ringing was created that he burned out his MOSFET several times. I have in one of the other pictures on the right-hand side, there's an example what, for example, ringing looks like. And you can see that the resulting voltage is by far overshooting the normal voltage, the intended voltage of the pulse. So usually when designing or when creating drivers and designing with MOSFETs, it is always a good idea to very generously increase the voltage, the maximum allowable voltage for that MOSFET to avoid immediately burning out the MOSFETs if something like that happens. Modern microcontrollers often provide options to adjust the switching speed of GPIO pins for low EMI designs. That is unrelated to the driver, but I just wanted to mention it. That microcontrollers, modern microcontrollers, like the STM32 series, allows for the option of changing the pull-up and pull-down speed of its output pins because of the EMI, of possible EMI, electromagnetic interference. So generally, somebody should only choose the highest possible output speed, output edge, if it is really needed for the purpose. Okay, next slide, please. I wanted to mention load fault conditions because that is something we have external loads. We want to connect these external loads. We have motors, we have lights, we have all kinds of external loads. And usually you connect them with, for example, just 2 wires. If it's a standard electric motor, maybe 3 wires. So there are fault conditions that are happening. And the driver circuits often need to be able to either detect the fault conditions before any power is applied, or at least detect the fault condition when power is applied. And they have to detect, the driver circuit has to detect this. The microcontroller has to check for a fault condition, and if necessary, set error flags or take the necessary steps. In automotive applications, usually there are always driver circuits that are capable of detecting a number of fault conditions, and the microcontroller or the processor in the engine control unit will check for these fault conditions and, if necessary, log these faults for the mechanic later to examine. So the 3 basic faults, like this is really just a very, very basic, there are many other fault conditions, but the 3 basic faults are open circuit, short circuit to ground, short circuit to supply voltage. There is nothing magical about it. I just wanted to mention these fault conditions. Different types of driver circuits can detect some or all of these error conditions. Okay, next slide, please. Okay, now I'm getting to the devices that we are going to use to control external devices. I'm starting with the simplest of them, relays and contactors. Relays are old, they are everywhere, they're easy to get, they're cheap. They're rugged, they're electromechanical, they are insensitive to overload on both ends. If you accidentally, for example, drive a 12-volt relay with 24 volts, it will not instantly burn out. If you, on the other end, if you overdrive a relay that is intended for 5 amps, if you overdrive it with like 6, 7 amps on the main contact, it will not immediately burn out. So this is different from electronic devices, which will happily get destroyed the moment that their maximum allowable values are exceeded. The other thing that a relay can provide is a so-called dry contact, an isolated contact, and because in general the relay contact is a metal-to-metal connection, it has a very, very low on resistance. And I'm writing here our audio-visual feedback in operation and fault. Of course, that is a little bit of a euphemism. What I really mean is that you can hear it clicking, and often you can hear or see if it is overloaded. For example, if you're switching an inductive load with a relay and you forgot the flyback diode, you forgot to protect the relay contact from the high voltages that an inductor can generate, you will see a spark. You can see a spark across the contact. If the relay casing, if the relay package is see-through, if it is in a transparent package. Widely available and cheap, I mentioned that. A relay is an inductive load by itself and cannot be directly driven by a microcontroller. If you see in the upper right-hand corner the first picture, this is what usually happens, how you usually drive a relay from a microcontroller. So you use a BJT, a bipolar junction transistor, which will be the next on the next slides. You use another switching element that can be directly connected to the microcontroller, and use that in a low side drive configuration to switch the relay. And in the image, you can also see the flyback diode that essentially avoids the high voltage that otherwise might destroy the transistor. This diode always has to be there in some form. It is an electron and requiring a flyback diode. A relay is typically triggered by DC voltage. Relays usually are meant for DC, 5 volt. The highest relays are like maybe 48 volts. 5 to 24 volts are the most common relays. And 5 volt, 12 volt, 24 volt is also really, really common relays. The coil power for a standard relay that can switch 15 to 40 amps or so is 200 to 500 milliwatts. The power switching capability of relays, automotive relays, are relatively easy to find and still reasonably cheap, up to a power range of maybe 40 amps. Standard industrial relays, a normal value for the switch is in the range of 10 amps to 15 amps, like 15 amps. Contactors. Contactors are the same idea as relays, but they're named differently because they are mostly intended for industrial applications. They're optimized for high voltage operation beyond 48 volts, beyond 24 volts. You can get 24 volt contactors, but the typical contactor that you're going to see is most likely something that you can see in the upper right-hand corner, one of the other image that I put on there. Whenever you see like a typical industrial setup, where you have like a green push button and you have a red push button, and the green push button turns on a big, three-phase motor, for example, generally there is a contactor behind that setup. Because contactors use high voltage for their trigger mechanism. Generally, if you want to switch a contactor from a microcontroller, you will have to put a relay in between, some form of relay in between. This could be a solid-state relay. However, you cannot drive a contactor directly from a microcontroller, not even with a transistor in between. You can do switch a relay from a microcontroller if you use a transistor or a MOSFET. Yeah, next slide, please. Solid-state relays. So because relays, the standard electromechanical type, were so common and versatile, the industry tried replicating the relay functionality with solid-state semiconductor devices. The solid-state is really just a different name for semiconductor devices. They combine the advantages of electromechanical relays, isolation, good connectivity with the advantage of semiconductor technology, lower speed, or lower power speed, no contact wear. A mechanical relay can wear out. They are really good, like they can usually sustain hundred thousands of switching cycles. However, they do have contact wear, and solid state relays do not. Solid state relays can run, they can work forever, forever. Solid state relays use optical isolation, and they can be driven directly from a microcontroller output. Optical isolation means that on the switching or the on one side of the solid state relay there is an LED, and the LED usually does not require more than maybe 20 milliamps, usually a lot less, 5 to 10 milliamps of power to fully activate the solid state relay. 5 to 10 milliamps, even 20 milliamps, can be provided from a microcontroller. The LED voltage is generally around 2 volts, which can also be provided from a microcontroller. Most microcontrollers nowadays run on 3.3 volts. That leaves enough room to switch a 2-volt LED. Solid state relays are more expensive than comparable electromechanical relays. It's just because electromechanical relays are just everywhere. They're being produced in huge numbers, and that makes them cheap. Solid state relays do not require a flyback diode. There is no inductor inside a solid state relay. So there's no flyback diode required. It can be switched directly from a microcontroller. Small solid state relays are available in similar packages as optocouplers. So unlike the solid state relays in those images up there on the upper right hand corner, they are surface mount devices. You can get solid state relays as surface mount devices. And if you look at the data sheet for example, the TLP 240, the AQY 280, which I had mentioned there, you will see the packages that these are available in. And especially the AQY series of solid state relays it is not just one chip. There's a whole series of different solid state relays in different voltages, in different current ratings, up to several hundred volts, low currents, of course. So there's a whole bunch of small solid state relays available, and they are relatively cheap. Like they do come in below $1 prices. Okay, next slide, please. Bipolar transistors, or more actually bipolar junction transistors. I'm not going to explain the actual working of a bipolar junction transistor in detail. They are standard. There's a lot of information out there on the internet about how they work. I just wanted to point out like some of the characteristics of these and the basic functionality. Bipolar transistors are current amplifiers. A small amount of current flow between a base and emitter creates a larger amount of current flow between collector and emitter. That is just the working principle. The voltage that needs to be achieved to create this current flow is 0.6 volts. This is the standard voltage for a PN junction. That is the voltage between base and emitter. This is not an unusual voltage, like all silicon PN junctions have this voltage. I'm putting it in here because what this does, or what this means, is that even very low power microcontrollers can switch bipolar junction transistors. The transistors are not obsolete, but they're old components. But they're still around. Most of the higher power transistors have been replaced by MOSFETs, and I'm going to talk about that. But The bipolar junction transistors never quite go away because they have some characteristics that makes them still very usable in circuits with microcontrollers. And one of these characteristics is the basically low voltage that is needed to turn them on. And that is about 0.6 volts. So even, for example, if you have a very low power circuit that is running off a coin cell, let's say like a CR2032 3-volt coin cell, many microcontrollers can go as low as 1.8 volts in their supply voltage. The digital logic that we have just discussed, the HCMOS logic, for example, can go as low as 2 volts in supply voltage. So it's entirely possible that you have a circuit that is operated from a coin cell that is sitting somewhere far away from any, that is monitoring something, or it is waiting for some event to happen to trigger it. And it is running at 3 volts. The coin cell is being discharged slowly. The coin cell is going from 3 volts nominal to 2.5 volts to 2 volts. If that event happens, then a bipolar transistor can still be used to switch some external devices, to switch some external event that has to happen. It is very difficult to find a regular MOSFET, like a standalone MOSFET that can act at these low voltages. A bipolar junction transistor can. For power MOSFETs, the usual gate voltage is up to 10 volts. Logic level voltage, logic level MOSFETs, and you're going to talk about MOSFETs. Logic level MOSFETs usually start conducting at 2 to 3 volts, and then they need to be significantly higher to actually achieve their design resistance, their design capabilities. So that's one of the advantage of bipolar transistors. There are NPN and PNP transistors. They kind of do the same thing. The PNP transistor just has the opposite voltages for everything. The NPN transistor is by far the most popular transistor for switching applications. Usually all low-side drivers use NPN transistors. The collector current is proportional to the base current. We mentioned it is a current, or I mentioned that it is a current amplifier. This is a gain factor. So it is proportional. A small base current, it creates a larger collector current. Both currents end up in the emitter. However, the gain factor, the ratio of smaller base current to bigger collector current, that is called the gain factor. It varies widely between transistor types, collector currents, and temperature. That's a problem. Transistors, when you buy transistors, they're usually grouped into gain groups, into HFE, that's the abbreviation for the current gain. And those groups can be, for example, something like 250 to 400. It varies that much. So in analog circuits in the past, a lot of circuit tricks had to be done to make the transistors usable for analog circuitry for amplifiers and stuff. In our case, we don't want to use the transistor as an analog device. We want to use it as a switch. So we need to do something special, or not something special, but we need to pay attention to how we're driving the transistor to guarantee that it works well as a switch. That will be in the follow-up slide, but I'm just finishing off this slide here. Transistors can be driven from low voltage microcontrollers. I've mentioned that. There's a relationship between the current, the collector current, and the gain factor. And generally, the higher power a transistor is, the lower its gain. as a transistor type that you can purchase in the store. So that's a problem, to the point where at a time in the past, in the 70s, 1970s, 1980s, when the transistor was really the only component that could amplify, that could be used as a switch when the MOSFETs that we have today were not available, that people used high power transistors that had a gain of 10 to 15. That means if you were trying to switch a current of 10 amps, you had to push 1 amp into the base of that transistor. So one transistor wasn't enough. You needed 2 or 3. You needed a sequence of 2 or 3 transistors with terrible efficiency. These high power transistors, like one of them is, for example, the 2M3055, they're still around because a lot of old circuitry is still around. You can still purchase them to repair old circuits, but nobody would use these transistors anymore for high power applications, simply because they're not efficient. Transistors cannot be paralleled without additional circuitry and efficiency loss. That is another thing, that's another negative thing about transistors. What I mean here is, normally you could say, well, if this smaller transistor is so much better, has so much better gain, why don't I just use 10 of these smaller transistors and put them in parallel? And you can't do that because the gain is very heavily temperature dependent. The lower the temperature, the worse the gain. Up to half. If you look at the data sheet, for example, and you look for any given transistor at the gain for 25 degrees Celsius, you get to a point, for example, where it's 100. I'm just taking a value. It's value of 100. And you look at the data sheet, you look at the curves for different temperatures, and the gain at minus 40 degrees might just be 50, approximately half. So the gain is very temperature dependent. That also means the gain increases with temperature. And that's why transistors cannot be paralleled without additional circuitry. Because it means if you have a number of transistors in series, one will always be better. Just because of tolerances, just because of manufacturing tolerances. The transistor that is best will have the higher gain than the other transistors. It will start conducting better, it will start conducting more current. If it starts conducting more current amongst the set of transistors, it will get hotter. If it gets hotter, the gain increases. It will start conducting more current, and so on until it burns out. So transistors can be paralleled with additional circuitry, which in this case is emitter resistors, to avoid to counteract this effect. However, if you do that, you get an efficiency, you get a big efficiency loss. You're burning off extra power in those emitter resistors. But if you're looking at all amplifiers, you will still see those kind of constructions, those kind of circuits, because for a long time, transistors, bipolar transistors, were the only option for high power circuits. Bipolar transistors can be extremely cheap. The standard bipolar transistors, low power standard NPN, PNP transistors, they can be as cheap as a cent. They can be almost as cheap as a resistor, depending on where you get them, depending on where you buy them. So that's another item that makes bipolar transistors still the choice for a lot of circuits, simply because they can be, if you pick the right component, they can be very, very cheap. It is not unusual in today's consumer and commercial circuitry to see bipolar transistors in circuits, like tens, dozens, maybe hundreds sometimes, of bipolar transistors in a circuit that could be replaced by a single gate or by a single integrated circuit that is especially made for that purpose. And the designer used transistors because, as an example, that specific circuit costs $2, but 20 transistors cost 50 cents. So you will still see in commercial devices that bipolar transistors are being used extensively because they can be very, very cheap. They're available from many, many sources. And as the last item here, for load currents more than roughly 1 amp, probably more like half an amp to 1 amp. If you need more power than that, MOSFETs are usually the better choice. There are some very cheap and powerful logic level MOSFETs available now, which I will be showing some examples later in a later slide. So generally, for switching relays, for switching small lamps, for switching small displays, transistors are a good choice. Bipolar junction transistors are a good choice. But if you get into a higher power requirement, it is almost always MOSFETs that are the component of choice. Okay, next slide, please. Bipolar transistors as switches. So in this case, in the image on the right-hand side, this is a sample circuit of how to use a bipolar transistor as a switch. There is a current limiting base resistor. There is the actual load, the collector resistor. Both in this case are 1 kilo ohm. It kind of depends how you calculate them. I just wanted to talk a little bit about some characteristics of the bipolar transistor when used as a switch. To me, the first item is the base saturation. So to minimize the collector emitter voltage in on state, a bipolar transistor is driven into base saturation when used as a switch. That is most of the time being done. It doesn't have to be done, but most of the time that is the best solution. This minimizes transistor steady-state power dissipation. Saturation in this context means that the base current is forced higher than the actual collector current requires at a given gain factor. So basically, what I'm trying to say is, let's say the transistor has a gain of 100. So technically, if I push in 1 milliamp into the base, it could switch 100 milliamp at the collector. But I want to make sure that the transistor is in saturation. So instead of instead of calculating the base resistor in a way that I'm pushing in 1 milliamp, I'm pushing in 5. So the transistor is definitely switched on, even if I'm just trying to switch 100 milliamps. The collector emitter voltage is, so if that is not clear what in this context saturation means, basically I'm making the base resistor smaller than necessary. The collector emitter voltage, that is essentially the switch voltage when the switch is on, is non-linear because it effectively crosses two PN junctions. It is not possible to bring it to zero. Typically, for smaller transistors in the range of a few hundred milliamps, it can go as low as like 0.2 to 0.5 volts. High power transistors might have a collector emitter voltage of up to 1 volts. This is a problem if you have a lot of current, because that voltage multiplied by the current directly translates into waste heat in the transistor, in the switch. I mentioned the saturated base before. One side effect of this, so for us it is desirable to saturate the base. But the problem is that the base is of the transistor, the junction of that transistor, is now flooded with charge carriers. And it takes a bit of time to burn those charge carriers off. So the turn-off time of the transistor will be a little bit longer than the turn-on time of the transistor. When I say a little bit longer, I'm talking about 200 nanoseconds to a microsecond. So if you're using the transistor to switch a relay, it absolutely does not matter. For a relay, 200 nanoseconds or 1 microsecond makes no difference whatsoever. But for example, if we're using the transistor in a different circuit, if we're using two transistors, and we are trying to counter switch them, turn one on while we're turning the other one off in a bridge configuration, this might be a problem because suddenly we have a microsecond where we are getting very steep current spikes. So this might require fixing in firmware. And if, for example, if you're using the two transistors like this in a bridge circuit, generally motor control timers as peripherals in a microcontroller allow for inserting dead time. So if you go through the data sheet for a timer component inside a microcontroller, and you see, for example, options for generating switching dead times, that's what that is for. To guarantee base saturation, the developer needs to review the transistor data sheet, estimate the gain factor for the intended collector current, and account for gain loss at low temperatures. So here, what I mean is, if you are trying to set the base resistor for the transistor, for example, you're intending to switch a relay. The relay has a current of 100 milliamps. That would be at the location where the RC, the collector resistor, is in the image. The transistor has, and you're assuming the transistor has a gain of 100. So you take the voltage of the microcontroller, which, for example, is 3.3 volts. You subtract the voltage of the PN junction, which is 0.6 volts. So now you're ending up with 2.7 volts. So you can expect the base resistor to have a voltage of 2.7 volts. And you want to push in a current of, let's say, 5 milliamps. So you take 2.7 volts divided by 5 milliamps. And the resistance value that you get is your new base resistor. And yeah, and never forget to basically halve the intended gain, or expect to operate the circuit at low temperatures, and compensate for the gain loss. And generally, it's about half at minus 40 degrees. It's just a rule of thumb. Okay, next slide, please. Yeah, I just wanted to go through some popular small signal resistors. All of these resistors are standard types. All of these resistors should be available at least the BC types should be available at Cosmodrome in Kharkiv. They come in different packages. I've mentioned the SOT23 package. I've mentioned SOT323, which is a smaller version, but the same pinout. TO92 version, it's a through-hole package that you can use on breadboards. So general purpose, small signal, high gain, partially very high gain for a transistor. NPN transistors, the BC847 as a surface mount device, the BC546 or 547 as a through-hole device, or standard types. The complementary, the PNP transistors, the North American typical transistors, MMBT 3904. The through-hole version is the PN 30 or 2N 3904. PNP version the 3906 have a little bit less gain than the BC 846s or 847. They're kind of older designs. However, each of those types should be available for very, very cheap at a local store in your city. General purpose small signal. These transistors are intended for somewhat higher voltages. If you only had space for one type of transistor in your box, in your prototyping box, I would say the BC817 or the BC337 in the through-hole version is probably the most versatile of them. They should all be very cheap. And if possible, to use, if it's still cheap enough, of course, I would go with the highest gain version. Each of those transistors of the BC family transistors is grouped into gain families, A, B, C. A has the lowest gain, B has medium gain, C has the highest gain. The C gain can be up to 800. So basically, with the C-type gain, you can input 1 milliamp and the transistor could switch 800 milliamps. Of course, it is not rated for 800 milliamps, but the gain is up to 800. Similar to the higher current transistors, the BC817, the gain grouping here is 16, 25, and 40. Where those numbers come from, I think it is just the maximum gain without a zero. So the 16 can have a gain up to 160, 25 up to 250, the 40 up to 400 gain. Power transistors, we're getting into a range here where MOSFETs might be the better option. However, sometimes you want to use, because for specific reasons, you want to use a bipolar junction transistor. If you're looking for like a 1 amp power type, the BCP56. There are other types. There was a BCX in a different package, the BCX56 in a different package. It's the same transistor, just in a different package. There are higher voltage types for transistors for 150 volts, for 300 volts. Generally, it used to be always easier to manufacture bipolar junction transistors for higher voltages. 300, 400 volts was not very difficult. So those are older devices. It used to be very hard to create MOSFETs for higher voltages. That has changed. But these MMBTA 42, MMBTA 92, those devices have been on the market for a long time. And I'm mentioning the obsolete types power transistors simply for the reason because you might see them in old schematics. If you go online, you search for schematics for a specific purpose, and you see like an old schematic that does exactly what you want from the 1980s or even 1990s. Those might still use those BD transistors. They might be using the 3N3055. The 2N3055 used to be the standard power transistor. It is big. It is designed to be directly screwed onto a heatsink. It is basically a heatsink by itself, and it used to be very popular. So you might be seeing it in different applications and different schematics. Yeah, I could. The BC abbreviation, B simply means it's a silicon, not a germanium transistor. The C means it's a small signal transistor. The D means, so BD is a silicon power transistor. All of these transistors should be available at Cosmodrome. Okay, next slide, please. How are we doing in time? Hello? I think I've exceeded my time.
Alexei writes about 15 to 20 minutes, Volker.
You mean I can continue for 15 to 20 minutes? Okay, yeah, okay.
But it's up to you. Up to you, but prefer time up to 20 minutes.
Okay. Yeah, I'm
Thank
sorry.
you.
This is getting I wasn't entirely sure when I made the slides, like how long I would be talking for each slide. Okay, I'll continue with the MOSFETs. I can leave the different driver circuitry for later. MOSFETs. So the transistors were basically current amplifiers, like a small current pushed into the base was creating a larger current from collector to emitter. MOSFETs are different. MOSFETs are effectively voltage-controlled resistors. You wouldn't use them as voltage-controlled resistors, but they have like a very small part of their diagram where you could use them. If you needed a voltage-controlled resistor, you probably would not use MOSFETs. You would use JFETs, junction field effect transistors. That's a completely different matter. But they're similar to that. A voltage applied to the gate reduces the resistance between drain and source. This is nonlinear. There are N-channel, P-channel MOSFETs, P-channel MOSFETs, and there are N and P-channel MOSFETs similar to NPN and PNP transistors. I'm writing this P-channel MOSFETs are inferior to N-channel MOSFETs. And I mean, I would be expecting, if this was a class, I would be expecting like an outcry. How can I say this? There are perfectly good P-channel MOSFETs everywhere. What I mean here is, as a combination of parameters, generally a P-channel MOSFET is inferior to a similar N-channel MOSFET. The way how it was explained to me is that in an N-channel MOSFET, the primary charge carrier are the electrons. In a P-channel MOSFET, the primary charge carriers are electron holes. Electrons are easier to move than electron holes. And the effect is that you can have P-channel MOSFETs that are perfectly good and that are almost identical to the complementary N-channel MOSFET, but either they are slightly more expensive because they needed to use a little bit more silicon material, or they have a higher capacitance, gate capacitance, which we're going to talk about. So amongst the, or they have like a slightly higher on resistance. So the P-channel MOSFET, like if you take 4 or 5 of the main parameters of a MOSFET, and there are 4 equal, the 4 of these parameters, if it's the on resistance or the price, or the capacitance, the gate capacitance, or the voltage rating, if you take those parameters, a P-channel MOSFET would always be slightly inferior to an N-channel MOSFET. But you can have perfectly matched P and N-channel MOSFETs from an electrical point of view. However, the reason why I'm putting this in, that P-channel MOSFETs are inferior to N-channel MOSFETs, not really, but practically yes. The reason why I'm saying this is because generally you will find many circuits where people on purpose attempt to only use N-channel MOSFETs because of this. Because N-channel MOSFETs have a wider selection, they're easier to get, They are cheaper for the same values, for the same parameters. In general, you can have a third generation N-channel MOSFET that is worse than a fourth generation P-channel MOSFET. But in general, circuit designers attempt to only use N-channel MOSFETs. One effect of this, for example, is switching power supplies. If you're looking at circuits, at integrated circuits for switching power supplies, the vast majority, like 95%, you can right away tell that they're using an N-channel MOSFET as the internal switching element because they use a bootstrap capacitor. I will talk about that later, if given the time. The same thing with MOSFET gate drivers. If you manage to get to the MOSFET gate drivers, the high voltage MOSFET gate drivers are designed, also with a bootstrap capacitor, are designed to use two N-channel MOSFETs, not a P-channel and an N-channel, which would be the natural idea of using a P-channel for the upper side of a bridge and the N-channel for the lower side of a bridge, would be the natural development. And in many cases, this is being done for low power bridges. But you will find just as many times that designers will go through many circuit tricks to make it possible to use N-channel MOSFETs on both sides of the bridge. So when I'm saying P-channel MOSFETs are inferior, you can find perfectly matched P and N-channel MOSFETs for use in a bridge. But generally, again, N-channel MOSFETs do have an advantage somewhere in your grouping of parameters. MOSFETs have a parasitic body diode. This is not always displayed. For example, in the first image in the upper image on the right-hand side, where it's showing basically a low side and a high side driver, you can see that there's no integrated parasitic body diode shown. It's just purely the gate, source, and drain connections of the MOSFET. On the other hand, the other two images in the middle and on the lower end, on the lower side of the slide, they do show the integrated body diode. It is always there, and sometimes it's good that it's there. Sometimes if some designers are cheaping out, especially if you get into BLDC motor drivers that are like cheap brushless DC motor drivers for drones, for example. And the designers for these motor controllers, for the BLDC motors, are trying to save money at every corner. They are trying to be as cheap as possible. They basically use these built-in body diodes of a MOSFET as flyback diodes for the motor. Typically, if you use bipolar junction transistors in a bridge circuit as a motor driver, you need to supply these flyback diodes in addition to the actual drivers, in addition to the actual switching device. And ideally, you should be doing that with external diodes for MOSFET bridges too. But these cheap Chinese motor controllers, usually they just say, okay, the body diode is good enough for this purpose, and they do not put any additional diodes into the circuit. And they work. So I can't really complain about that. I can complain about other items. The current rating on those motor controllers is sometimes absolutely ludicrous because they don't have any heat sinking capability. But that is a totally different item that we might talk about later. They have a parasitic body diode. So even if it's not in the image, it is there. MOSFETs do not use power in steady state on or off condition. That is important because if you're turning a bipolar transistor on, it will consume power. In order to keep the current flowing, you need to push in the base current. For MOSFETs, that is not necessary. MOSFETs are voltage controlled. Once they're switched and the voltage on the gate terminal is maintained, they will stay on without consuming power. MOSFETs can be paralleled. They have the opposite behavior than the transistors have. If they get hotter, the resistance increases, so the other MOSFETs in a parallel setup take over. Usually, it is rare to see MOSFETs paralleled, even though you could, simply because there are so many different MOSFETs on the market in very, very high power ratings that it is almost never necessary. You can find MOSFETs for hundreds of amps. And depending on the package, some MOSFETs are rated for currents because their on resistance is so low, 3 milliohms, 4 or 5 milliohms in on state, in full on state, that effectively the package terminals have a higher resistance than the silicon in the MOSFET. At that point in time, seeing a 150 amp rated MOSFET in a TO220 package is a little bit concerning because a TO220 package is the package in the image in the lower right hand corner. That is a TO220 package. So seeing a 150 amp rated MOSFET in that package is concerning because the package isn't really rated for that. You might be able to use it, but you would have to provide a lot of heat sinking on both sides of the connection. The MOSFETs can be paralleled. High power MOSFETs require a gate voltage of 10 volts or more. So the first MOSFETs required 10 volts or more. The first to third generation MOSFETs needed a higher voltage than a microcontroller can provide. Even a 5-volt microcontroller cannot provide the voltage required to fully switch the MOSFET. So a gate driver is required, some sort of gate driver is required. Nowadays, they improved the MOSFETs, and you can get logic level MOSFETs that have a gate threshold voltages where they start conducting starting at 0.9 volts. Those are not very typical, but you can get them, usually not for high power, only for small signal. So it is possible to use MOSFETs like that directly driven from a 3.3 volt microcontroller, and they will work fine. But again, not for power applications, not for motor driver applications. A MOSFET gate can have significant capacitance, and that is really the important point here. So normally, when I'm telling you that a MOSFET can be turned on without using power, the first question would be, why are we still using transistors? Why aren't we just completely switching over everything to MOSFETs? The problem is the gate capacitance. We're trying to use the MOSFET as a switch. We're trying to use the MOSFET as a switch at high frequencies. Because we need a high frequency to power the motor without the motor vibrating. We need high frequencies for lighting, so hundreds of hertz in this case, that is not that high of a frequency. But we do need PWM circuits in the kilohertz to hundreds of kilohertz range, depending on the gate. For switching power supplies, switching frequencies of 500 kilohertz to 2 megahertz is not unusual. So the problem is now with that gate capacitance, you need to charge and discharge the gate in order for the MOSFET to switch. And so you need to treat the gate of the MOSFET like a capacitor. And you need to very quickly, in order to minimize the power dissipation, the power waste in the MOSFET, you need to switch very fast the gate from 10 volts to 0 volts and from 0 volts to 10 volts. That is more than a microcontroller output can do, even if the voltage was higher. So generally, a MOSFET, if you want to operate it efficiently, it requires some kind of gate driver circuit. Luckily, there are many gate driver circuits available, even if you don't use a specific gate driver circuit, if you don't switch very often, sometimes it is sufficient to just use a resistor, like a pull down resistor in this case, between gate and source, to discharge the gate if necessary. This, of course, would have the effect that it is very fast to turn on the MOSFET, and it takes a long time to turn off the MOSFET. Again, possibly requiring compensation in firmware when through dev times when setting up the PWM peripheral on a microcontroller. Gate capacitances that I'm mentioning here is, for example, very small N-channel MOSFETs. For example, in the image in the middle, you can just barely see that is supposed to be a 2N2000. Gate capacitances are in the tens of picofarad, so that is not a problem to drive from a microcontroller. However, they very quickly go into the hundreds of picofarads, which is beyond what a microcontroller pin or a logic pin is rated for. They can, for power MOSFETs, go into 4 nanofarads to 10 nanofarads for the really high power MOSFETs, which are still cheap. There are still cheap devices. They can still be cheap devices if you pick the right one. So for those MOSFETs where you have 10 nanofarads of gate capacitance, and you're trying to charge and discharge this gate capacitor effectively at frequencies of 100 kilohertz, you need a significant amount of gate driver capacity. A MOSFET gate cannot be left floating in microcontroller reset. I wanted to put that in because this is for practical circuit design. And if you use a transistor as a switch and you connect it to a microcontroller, just the base resistor is good enough. In reset, when the pin is floating, is basically disconnected. When the microcontroller resets, the pin is disconnected, and the transistor does not get its base current, so it does not turn on. However, if you're doing the same thing with a MOSFET, the MOSFET can pick up stray EMI, it can pick up radio frequency interference of some sort, and it can float high. And it can accidentally turn on when the microcontroller is in reset. And that can be a very subtle problem that creates catastrophic consequences. If the microcontroller, you make a software error, a firmware error, the microcontroller the watchdog circuit kicks in and forces a reset of the microcontroller. During the reset, all pins on the microcontroller go to high impedance mode. And now you have a load switch. You have some kind of device that is turning on a motor that is connected to a MOSFET. And now the MOSFET gate floats up. The MOSFET turns on. The motor turns on and might harm somebody. So that is a major problem. So you have to be always aware that a MOSFET needs a pull-down resistor. Sometimes, or most of the time, it also needs a gate resistor if you want to limit the gate current from the microcontroller, but you also want to put in a pull-down resistor so that in high impedance mode, the gate, the MOSFET, is not accidentally turning on. So where you need one resistor for a transistor circuit, you need to implement two resistors for a MOSFET circuit. This is not a problem, resistors are dirt cheap. But when you're designing your circuit, never forget the pull-down resistor for a MOSFET. Of course, it can also be a pull-up resistor, but then it would be turning on in reset, which in most cases is not desirable. However, it cannot be left floating. It needs to be pulled into some kind of defined state. Oh yeah, and another item is the RDS on. So RDS is the resistance drain source in on state. That's what the RDS on stands for. This is a value that's in the data sheet under different gate voltages. Read the data sheet. It is super interesting how the different MOSFETs, what their characteristics are. It's negative proportional to the gate capacitance, and I have mentioned that basically the the more powerful the MOSFET is, the lower the on-state resistance is, the more current the MOSFET can carry, the higher the gate capacitance is. To the point where if you have a MOSFET that can switch 150 amps, you might end up with a gate capacitance of 10 nanofarads. They are continuously being improved. The latest generation MOSFETs might just use 5 nanofarads. Look at the data sheet. Okay, next slide, please. MOSFETs as switches. I talked about a little bit about that. I have the same image here again. Really, MOSFETs, you will only use them as switches. It is really their primary purpose. That's what they're being sold for. The data sheet will specify the on resistance. I've talked about the on resistance. You supply a certain amount of voltage on the gate. This will result in a low resistance between drain and source. The gate threshold voltage indicates when the MOSFET starts conducting. There is a lot of information about MOSFETs on the internet. Basically, the exact working principle you can find everywhere. I'm just trying to point out certain values in the data sheet that are important for your circuit design. I've mentioned the large gate capacitances. MOSFET are used in fast PWM applications. The gate capacitance to be charged and discharged quickly. And in many cases, the logic outputs from a microcontroller or from a gate cannot drive, or from a logic gate cannot drive the gate terminal of a high power MOSFET directly. A driver circuit is required. Okay, next slide, please. MOSFET examples. Here I was trying to replicate what I did for the bipolar junction transistors. Basically, if you only have one space available in your prototyping box for a small signal MOSFET, I would suggest get the BSS 138. It is a logic level MOSFET. It is not really intended for 3.3 volts. It is a logic level MOSFET for 5 volts. But if you really need a MOSFET that you directly attach to a microcontroller instead of a junction transistor, then that is probably the type that you want. The FDV 301 is a good choice. The 2N7002 is a popular MOSFET, but it really only works for 5 volt. It is not really good enough for 3.3 volt. The FDV 301 is better than the BSS 138 in terms of gate threshold voltage, but it is more expensive. It has the same. All of these have the same package and the same pinout. So you could replace them if you're doing a board layout. You could replace them, and if one doesn't work out, the FDV 301 and there are a number of very low gate threshold voltage MOSFETs. These are just ones that you could technically directly connect to an output from a microcontroller because the gate capacitance is very low. It is just a few picofarads, and you don't have to worry about creating a too high of a capacitive load for the MCU output or the logic output. The next level here, those are newer MOSFETs. The AO3400A, the P-channel version, the 3401A, these are modern MOSFETs. They are perfectly usable at 3.3 volts. The gate threshold voltage is also very low, and they can be used for a considerable higher current. The BSS 138 is, I think, rated for about 200 milliamps. The AO 3400 is, on the other hand, I think up to 5.7 amps, which is kind of, again, one of on the iffy side, because the silicon, the actual MOSFET die might be rated for that, but it is an SOT23 package MOSFET. It is the same package as the BSS 138. So you have to be really, really careful not to overheat that package because it has no heat sinking capability. I think it is rated for about 300 milliwatts of power dissipation. So the MOSFET itself might be rated for 5.7 amps, but really don't push it that far. High power MOSFETs. Basically, there are hundreds and thousands of different types of power MOSFETs available. Older ones, newer ones, cheaper, more expensive, N-channel, P-channel. You will have to basically look what is available and what is cheap in your area. In this case, I picked two MOSFETs that were available at Cosmodrome and were cheap. These two, the IRLR, the L is for logic level, so it is a fairly low voltage MOSFET. I think the lowest RDS on, the lowest, or the highest power rating, the lowest on resistance is still for 10 volts of gate voltage. The AOD 403, there are other MOSFETs, N-channel MOSFETs from the same AO, Alpha Omega company, from the same line. I picked the IRLR 8726 because it was cheap at Cosmodrome. It is somewhat mostly evenly matched with the AOD 403. So if you needed to build a P and N-channel bridge, for example, a motor control for driving a BLDC motor, that would be two possible MOSFETs to get. They are very cheap. Okay, next slide, please. MOSFET gate drivers. MOSFETs might require gate drivers if the gate voltage or switching speed exceeds the ability for microcontroller to directly drive it. For most microcontrollers and for most applications, for most high power applications, that will be the case. You need a gate driver. I mentioned the logic level MOSFETs that can be switched by 3.3 volts or 5 volts. However, if we're trying to move a three-phase motor, if we're trying to move a BLDC motor, those are motors that can consume 15 amps, 30 amps, no problem. That is not going to work with small MOSFETs. If you have large, powerful MOSFETs, the high capable MOSFETs, you are going to need a gate driver. And I just wanted to mention some gate driver principles here for this purpose. Just in case, if you look at the available gate drivers and you're confused, why are there so many different gate drivers? Or what is the difference between the gate drivers? So there's one type of gate driver that is simply a level shifter. It can have a P-channel and or N-channel MOSFET up to usually it's about 20 to 24 volt, some 18 volt, but basically they're intended for 12 volt operation for battery, 12 volt battery operated operation. A 12 volt battery can have up to 14.4 in overload conditions, in error failure conditions, up to 15 volts or so. Supply voltage from a 3.3 volt microcontroller output. Steady state operation is possible. I'm saying that I'm putting that in here because the other type of gate driver, steady state operation, is not possible. And I have to explain this. So these MOSFET drivers, they usually come in a SOIC 8 package, some in an SOIC 16 package, some in a smaller package if it's just a single gate driver. But the ones that I've listed here, they come in an SOIC 8-pin package. They're coming from a line of gate drivers that all do the same thing, that have slight differences, like some are inverting, some are not inverting. Some can supply up to momentarily 1.5 amps or 3 amps. The highest devices of that line, which I think is a 4429, can supply up to 9 amps momentarily. Not continuously, just momentarily, because the intended load, the MOSFET, will only need the high current momentarily at the moment of switching. Steady state operation is possible, so you have these TC4420. There are so many different manufacturers that make them, and each one uses a different shortfall. So in this case, TC is from Microchip. IX is from a different company. IR is from International Rectifier. There's a cause like COS. There are a number of different companies that make these. They have the same pinout, mostly identical parameters. They're cheap, or they can be cheap, depending on which one you pick. So what they do, they take the 3.3 volt microcontroller input, they translate it up to the supply voltage, 20 volts or so, and you can basically directly drive a MOSFET, a high voltage, like a 10 volt MOSFET that needs 10 volts of gate drive, with the output from these drivers. 3.3 volt in, and up to 20 volts out for gate driving. If you use these in a bridge configuration, and the last three that I've listed there contain two drivers in one package, and they're intended for bridge configuration, you would use a P-channel MOSFET in the upper part of the bridge and an N-channel MOSFET in the lower part of the bridge. And you can turn those on permanently. If you needed to, if it was, for example, for a stepper motor, as a driver for a stepper motor, you can keep the motor activated, you can keep the motor powered in one state as part of a full bridge, an H bridge. You can keep it on permanently. Even with or without PWMing, if you don't want to PWM the output, you can just turn it on permanently for a longer period of time. The second part, or the second type of gate driver, are level shifters, but they contain a bootstrap circuit for high voltage operation of two N-channel MOSFETs. What do I mean? That is the image that you see at the top. On the right-hand side at the top. You can see those two MOSFETs in that circuit, and they both have the arrow pointing inwards. That means those are two N-channel MOSFETs. Again, N-channel MOSFETs are generally preferred because they're cheaper and or more powerful and or have a lower gate capacitance. Somehow, in some way, N-channel MOSFETs always have a slight advantage over P-channel MOSFETs. So people like to use N-channel MOSFETs. So what you see there's a capacitor, there's a diode and a capacitor. And what happens here is that the capacitor is being charged from the supply voltage when the low side MOSFET is turned on, and then when the other MOSFET is being on, the capacitor is discharged into the N-channel MOSFETs on the high side. The capacitor voltage is essentially riding on the high voltage, and it needs to do that in order to turn an N-channel MOSFET on. In an N-channel MOSFET, the gate voltage needs to be higher than the source voltage. So you need a voltage that is sitting on top, that is basically riding on top of your supply voltage. That is the difficulty with using an N-channel MOSFET for a high side switch. If you used a P-channel MOSFET, the voltage needs to be lower. And that's not a problem. Creating a voltage lower than the supply voltage is not a problem at all. Creating a voltage higher than the supply voltage, that is a problem. And that is what the bootstrap capacitor is for. It charges when the low side MOSFET is on, and it discharges when the high side MOSFET is on. And it provides the high side MOSFET with the power to charge its gate. What is the problem with this driver? The problem with this driver is that it needs to keep switching. You can only use this driver in a switching in a PWM application. The capacitor, once it's discharged, it has discharged its capacitance into the gate of the high side MOSFET, it's empty. For the next switching, it needs to be charged again. So it needs to, the low side MOSFET has to turn on again. Otherwise, if you try using it in a steady state application, the gate charge of the high side MOSFET would slowly bleed off, and it would not turn on anymore, it would not switch anymore. So you need this type of gate driver, or even high side, even if it was a standalone high side driver, you need this type of driver circuit that uses a bootstrap circuit with a bootstrap capacitor. It needs to keep switching. I have mentioned, for example, independent from this, I have mentioned switching power supplies, that there are integrated chips that are basically switching power supplies that are using an N-channel MOSFET for the switching power supply, and that have a bootstrap capacitor. That's pretty much all of them. The problem with these switching power supplies is the same problem that these gate drivers have. It is essentially the same circuit. And the problem is they cannot operate at 100% duty cycle, meaning when the supply voltage approaches the voltage of the output, it cannot simply turn on the high channel, the high side MOSFET. It has to keep switching, it will drop the output voltage much below the lower supply voltage. There always needs to be a voltage differential between these two. Voltage regulators, switching voltage regulators with a P-channel switching element do not have that problem, but they almost don't exist. There's one line that I know of switching voltage regulators, and that is the line around the L5973 that has a P-channel MOSFET as a switching element. And that is a nice to have in your repertoire, in your little box of tricks, if something like that is required. If you have a situation where you need to output 12 volts, powered from a battery that is at 14.4 volts, but slowly discharges and goes towards 12 volts, an N-channel based voltage regulator can't do that. A P-channel MOSFET based voltage regulator can. It will simply turn into a low drop linear regulator when it approaches the 12 volt output voltage. This is probably too much information. That's the second type of gate driver. They are extremely popular. They're cheap. Popular examples are, for example, the IRS 2101, the IR 2104. They are in use for high voltage circuitry. You can get this type of gate driver for voltages up to 600 volts for definitely high voltage operation. It is almost more difficult to find MOSFETs, cheap MOSFETs that can operate at these high voltages. Gate drivers that are leveraged and use a charge pump. Okay, so now how can you avoid having to continuously switch? In motor control applications, providing a constant PWM is not really a problem. In other applications, it might be. So now you want to combine these two. You want a gate driver that is both a level shifter. It doesn't need to be switched all the time. It doesn't have the bootstrap capacitor. And that would be a charge pump. Basically, something that can use, there are also some other technologies that use an inductor for this, that create a voltage that is basically riding on top of the supply voltage for the N-channel MOSFET. However, these types of gate drivers are rare. They're not typically being used. They're very specialty. And I just wanted to mention that they exist. Really, the two most popular gate drivers are these two types, the first two types. Okay, next slide, please. Transistor MOSFET packages. There are way too many packages available that I can mention here. There will be a whole different presentation if I talk about, if I mention all the different packages and the characteristics. I just wanted to mention a few items here. MOSFETs as newer devices, you can't get them in older, really old packages like TO3, for example, which is the package of the 2N3055. The package heat dissipation capability directly affects the device's current rating. And I want to point that out here. Two MOSFETs with the same RDS on, if two MOSFETs, the same silicon, but in two different packages, will have different current ratings. The MOSFET actual material is the same, but they will be rated for a different maximum current depending on the power dissipation capability of the package. So that is one item. The other item is that you can buy MOSFETs that could dissipate, like based on the package, a certain amount of power as heat. But you need to supply the heat sinking capability around that MOSFET to actually use it at the rated power. I see that very often, especially again from like motor drivers, from cheap motor drivers from AliExpress or other places where people use as a MOSFET rating to advertise their product. So they use a MOSFET that is rated for 80 amps, and they advertise their product as a motor driver for 80 amps. And of course, that is complete nonsense. Because, for example, I've seen motor drivers that are grouped. You have 6 MOSFETs, you have 3 half bridges, you have 6 MOSFETs on a tiny, tiny circuit board. And the MOSFETs are the ones that you can see in the upper right-hand corner in a TO252 package. The package would be able to dissipate 50 watts of power or more of waste power that happens, that would occur if you use the MOSFET at its rated power. The package would be able to dissipate that power, but you're not providing the heat sinking surrounding the package. So if you actually tried using that motor driver at the advertised current rating, it basically would turn into a glowing supernova because it cannot get rid of the waste heat. It cannot dissipate the waste heat. So that is something to pay attention to. Just because a MOSFET is rated for a certain amount of current doesn't mean that you can actually use it at a certain amount of current. Always pay attention to the actual heat sinking capability surrounding the MOSFET. And that is more or less a mechanical issue. Common packages, I've shown some packages there. The TO220 package is the one in the middle, and actually the TO247 package, that is one of the largest. It is not shown here. It is one of the largest through-hole packages, and it is a good package if you want to attach a transistor or a MOSFET. If you want to attach a MOSFET to an external large heatsink, the TO247 package is one of the best options for that. It is rated for a considerable amount of power and current capability. The surface mount package is SOT23, that is the upper left picture, TO252, also called DPAC. It is the package on the upper right-hand corner. But again, MOSFETs can come in a variety of different packages that are more or less convenient to use. The same MOSFET can be available in a number of different packages. For example, the TO252 package requires a heat sinking area that you might not want. If you're saying, yes, you're using that MOSFET because it has this very, very low RDS on, but you don't actually want to run it at 80 amps, and you don't expect it to dissipate a lot of power, then you might be better off with a similar MOSFET in an SO8 package, which is technically, it's an integrated circuit package for gates or op amps, but you can buy MOSFETs in an SO8 or SOAC8 package. Okay, next slide, please. Thyristors and triacs. I wanted to at least mention these. Those are very classical, or not, those are old components. They were the first components that were commonly used and are still being used primarily in AC switching. They are from a time when after the transistor was invented, and the researchers were discovering the characteristics of a PN junction, and they were just experimenting. And so the diode is one PN junction, a transistor is 2 PN junctions, a thyristor is 3 PN junctions. It is a device that is basically triggered once and keeps conducting. And normally you would think what good is that? Like you can only use it once as a switch. What is happening with thyristors and triacs is they're used in AC circuitry. They keep conducting once triggered until the supply voltage goes to zero. And that resets them. So that makes them ideal for AC, for alternating current applications, because in alternating current applications, the supply voltage is being pushed to zero all the time. Twice per period, you're hitting 0 volts, and that resets the triac. A triac is essentially two anti-parallel thyristors, so that it can be fully used for AC. They um, they used to be very popular. They are very popular. They are a perfectly good component if you need to switch AC voltage. There's a ton of information on the internet about triacs. It's an old device. Yeah, and most importantly, you can get them for very high voltages, like 1200 volts, no problem. The way how they're typically being used is they are being triggered um, as part of a phase cutting circuit, as within the AC waveform. That is the image that you can see on the right-hand side. The problem with that is it creates a lot of noise. It creates a lot of EMI, electromagnetic interference. That has been a problem since they were invented, like for the last 60 years or so, 50 years. And that's why you see in the schematic on the left-hand side, that is a very simple dimmer circuit for dimming light bulbs. You see that extra inductor in there. That is intended to reduce the amount of EMI. It's a choke, basically. It's intended to choke out electromagnetic interference. Okay, next slide, please. Okay, now we're getting to the driver circuits. Are you sure I'm still okay with the time?
More or less okay, Volker, but you'd better move to finish.
Okay, yeah. Okay, like the driver circuits are the end of the presentation anyway. Okay, low side driver, essentially, this is the equivalent of an open collector or an open drain output in the digital logic that I had mentioned earlier. So a low side driver switches the device to ground. This means that one end of the load, or it switches the load to ground. This means that one end of the load is connected to the supply voltage. This might have effects on the cabling that you're using. I will talk about that. This is generally the easiest way of switching a load. Low side driving is not the intuitive kind of driving, but with the technology that we have, it is the easiest type of turning on or switching a load. It is extensively being used. Some low side drivers are extensions of digital logic. What I mean with that is some of these drivers are directly intended to be connected to digital logic devices. For example, the ULN 2803, you will find plenty of schematics where that low side driver is, for example, directly coupled, directly connected to a 74HC595, a serial to parallel shift register. And as a continuation of that, the TPIC6C595, there's a range of similar chips available. That is a chip in the image on the upper right-hand side, is basically those two mixed together with MOSFET outputs. It is a serial shift register with parallel outputs The outputs are low side drivers, so open drain devices, and they can switch, I think, about 100 milliamps or so, enough for a relay. So these circuits are primarily used for driving lamps, smaller lamps, for driving relays is a big item. They're not intended as motor drivers. They are the ULN 2803, ULN 2003 are very, very cheap devices, especially the ULN 2003 is a very cheap device. It contains an array of 7 Darlington transistors, and it is used for relay driving everywhere. And they are low-side drivers. Some low-side drivers contain fault detection and overload protection. I put some examples here, BSP70, BSP76. These do not provide fault detection, but they do provide overload detection. They are essentially safe against failure if a short circuit happens. If the load is, if there's accidentally an overload, the load is sort of short-circuited to supply voltage or to ground, or if the output is accidentally connected with supply voltage, these drivers will detect this and will not burn out. They are more expensive than simple MOSFETs, though. Simple MOSFETs would burn out in those situations. These drivers won't, but of course, these are also more expensive. Low-side drive is the simplest and most cost-effective way. I mentioned that the switching component is usually NPN or N-channel MOSFET, always. Very high power switching is possible. I'm saying that because you can get N-channel MOSFETs in very, very high current ratings. 190 amps, 200 amps is absolutely possible. So if you have like a very high current, a very high power device that doesn't require much voltage, supply voltage, usually the high power MOSFETs are low voltage MOSFETs. You can get a MOSFET for that, you can get a low side driver solution for that. The connection to the load requires supply voltage in one cable connection. Additional fusing might be required. That's one of the drawbacks of the low side driver. As you can see in the image on the left-hand side, the right part of the image on the left-hand side, one side of the load is connected to supply voltage. That means you have to route supply voltage on a cable through, for example, a vehicle, if you're using a low side driver to turn something on in a vehicle. In most vehicles, the chassis is ground. So if the cable gets damaged, you would create a short circuit between supply voltage and ground. So in these applications, you would have to supply an extra fuse option to make this safe. Low side driving is unsuitable if the load requires a permanent ground connection for sensor connections. That is a biggie. That is a big problem with low side driving. That is why other drivers really exist. Putting an additional fuse in is not a big problem. But if you, for whatever reason, you need the load to retain a ground connection, because, for example, you're measuring a current, you have a shunt resistor on the ground, and you're trying to measure the load current, or you have a switch that is measuring rotation. There's any number of reasons why you might want to retain a ground connection to your load. In those situations, the low side drive is not suitable. It's fine for relays. It's fine for lamps. Okay, next slide, please. Okay, high side driver. So it's the same image that I have here, but this time you're looking on the left side of the circuit. So the high side driver is doing what is more intuitive. You're switching the supply voltage. Everybody understands that. The load retains a permanent ground connection, which allows for the connection of sensors. Um, yeah, there are a number of issues why you might want that. High side driving adds complexity and cost to the driving circuit. That is really the problem. If you try to just say, okay, how about I take my low side drive and I'm taking the same circuit and I'm just tying my load to the emitter of my low side driver and I'm tying the collector to the supply voltage. That doesn't work because the base or the emitter is always the voltage drop between base and emitter is always 0.6 volts. So if you're driving the transistor or MOSFET for that matter, from a microcontroller output, the voltage to the load can never be higher than the microcontroller voltage. That's not what you want. So you can try a few other possibilities are there. You could try to use a PNP transistor and hook that up, but that creates the same problem. You can do that without the disadvantage of the first solution if you use a PNP transistor, but you are still limited to the supply voltage of the microcontroller that you can switch, which in most cases is not what you want. If you tried hooking up a PNP transistor or a P-channel MOSFET to the supply voltage and then driving it directly from the microcontroller, you can't do that either because the microcontroller is a digital device. It's a digital logic device. In all cases nowadays, it is a MOSFET device. It has those two diodes. It has the two protection diodes on its output, which means the output of the microcontroller can never be higher than its supply voltage plus 0.6 volt of voltage drop from the protection diode. It is a clamp. The protection diodes are voltage clamps. So if you, for example, tied a P-channel or a PNP transistor to 12 volts, and you had a resistor, and you tied the gate of that MOSFET or the base of that transistor to the microcontroller, it would just be always on. And you could not turn it off. So that doesn't work either. So you need a level shifter, and you need a more complex design than a low side driver. The easiest or the least complex design is what's called a load switch, and that is on the next slide. And I think the implementation of high side N-channel MOS requires a bootstrap charge pump circuit. That is the next level of complexity. So the low side driver can be done with one MOSFET or one transistor. The high side driver requires at least two and possibly a lot more. Integrated high side drivers with gate driver and overload protection exist. This is equivalent to the protected low side drivers that I've just demonstrated, that I've just mentioned. BTS 5210, BTS 4140, they are of course more expensive than just their equivalent MOSFETs. They have all this complexity of the high side driving built into the chip, but they're more expensive. Okay, next slide, please. Okay, so this is for a high side drive. This is the easiest method. And you can see here where the low side drive is okay with one switching component, you need two switching components for the high side drive. This circuit design, a P-channel switch at the top and an N-channel switch or an NPN transistor at the bottom, that is called a load switch. If you just Google for the term load switch, this type of circuitry will pop up. Yeah, basically you are triggering Q1 from the microcontroller, and the microcontroller will activate the p-channel MOSFET by pulling its gate down. It works the same if you use a PNP transistor or a p-channel MOSFET. So you can implement this kind of high side drive with both technologies, with both transistors or MOSFETs. What is the problem here? The problem here is that the turn off of the MOSFET is done by R2. So you're actively turning the MOSFET on. You're actively turning the MOSFET on through Q1 and R1, and that is very fast. You are pulling the MOSFET off. Oh, the slide just switched. Thank you. You're pulling the MOSFET off through R2, and that is slow. So here again, we have asymmetric behavior. And depending on the values for R1 and R2, the turnoff might be very slow, too slow to be used for PWM. So this type of circuit can be used for slow PWM in the range of a few kilohertz, up to a few kilohertz, but more generally, it is used for permanently turning a device on or off. Integrated load switches are common, mostly for low voltages. If you just Google or if you just AI and you ask, show me a number of integrated load switches for 28 volts or for 30 volts or whatever, you will see there will be a number of responses. They are, again, more expensive than just the P-channel MOSFET and the N-channel MOSFET. The integrated load switches are, of course, protected against overload and overtemperature. The MOSFETs are not. Okay, next slide, please. Half-bridge. This is simply the continuation of a push-pull driver that we've seen in digital logic. Now we're getting into more functional motor driving. A half-bridge circuit, you can use a P-channel and an N-channel MOSFET, and usually you would do that if you're using one of the level-shifting gate drivers. If you're using one of the bootstrapping gate drivers, you most likely would be using two N-channel MOSFETs. If you're planning on PWMing, on using PWM for the motor drive, then both options are fine. For half-bridge configuration, gate driver is required simply because you want to operate a motor at 12 volts or 24 volts or even higher, not at 3.3 volts of the power supply of the microcontroller. A half-bridge circuit on a single supply cannot reverse the polarity, but it can actively discharge it, so you can do faster switching with it. As opposed to the from the previous slide, as opposed to the load switch circuit. A half-bridge circuit on 2 supply voltage can reverse the load polarity. That is the bottom image. You can see here the DC bus has a positive and a negative and a ground. And the load is connected to ground through a completely unnecessary capacitor, but it depends on the load. So in that configuration, it could reverse the polarity, but usually you would use a full bridge circuit for that, which is on the next slide. And I think that is the last slide. So for all kinds of for all kinds of real professional motor control solutions, you would be using a full bridge, H bridge, either combined out of 2 half bridges, or for BLDC motors out of 3 half bridges. If you combine it out of two half bridges, if you have an H bridge, you can PWM a motor. If it was a DC brushed motor, not a brushless motor, if it was a DC brushed motor, you can control the speed through PWM and you can reverse the rotation direction. That is a very classic application for an H bridge. You can use two H bridges and control a winding in a stepper motor. That would be a typical application for a stepper motor drive, and you can get integrated circuits that do this. For example, I've mentioned that here, the L298, that's actually two full bridges intended for a bipolar stepper motor that has two different windings, two different coil accesses, and it's an older circuit. The L298 is very common, so you have two H bridges to drive a stepper motor. For BLDC motors, you would not use, in most cases, you would not use an integrated circuit simply because they don't exist in the power levels that are required for BLDC motors. You would use individual MOSFETs and just design your circuit around three half bridges. You need the three half bridges to create a rotating field for the BLDC motor. How that exactly is done would exceed the terms of this lecture here. I'm way over time at the moment. If students are interested in finding out more, or if students have specific questions or design suggestions for specific topics, like a BLDC motor, like a stepper motor driving, or RC servo driving, I would be happy to find out or to create another smaller lecture or design a circuitry for that, so that students can test out the design concepts. Okay, I think that is the end of the lecture. That is the end.
Okay, Volker, thank you for such interesting and long lecture. It really important.
I'm so sorry about how long it got. Yeah, I couldn't stop, and I haven't even actually touched how the NPN and transistors work, or how the MOSFETs work. But there is so much information about the basic functioning available on the internet. I don't think it needed to be said in the lecture. If any students are interested in getting code examples for creating PWM, for setting up a small system, I'm happy to provide code examples. Like I've given you, I think a while ago, some code examples for the laboratory boards, for the lab boards, which unfortunately cannot be used in the current situation.
Thank you again. Maybe somebody have questions to Mr. Rademacher. Please feel free asking him.
Absolutely, yeah.
Okay. While they are thinking about questions, I have a question. Could I ask you? Volker, you have a huge practical experience. Tell me, please, maybe you've encountered in your practice some interesting or non-typical types of external devices to be controlled. Could you tell us about such devices if you have real cases?
Untypical external devices. Everything really that I controlled was somewhat tricky. Well, one example, which I might have mentioned in a previous lecture, I'm not sure. One example, for example, was we talked about stepper motors. When I was working on the fuel cell devices that I had mentioned before, um, the scientists working on these fuel cell devices were experimenting with liquid injection of certain liquids, like into the main reaction chamber, and because they wanted the very precisely dose the injection of these liquids, they used a medical pump. The medical pump had a tiny volume, and because the scientists were trying to um, determine the submitted amount of liquid in very controlled, very defined steps, they demand a stepper motor to drive this pump. Like normally you would drive this pump just simply with a brush DC motor, but they wanted to control the rotation. So we used a stepper motor and we created a stepper motor driver. The problem with that was that the pump, because it had this tiny volume, because it was meant for medical purposes, it needed to rotate at a very high rotation speeds, like almost too high for a stepper motor. We couldn't just turn on the stepper motor at that speed. We needed to ramp up the speed. During that ramp up of the speed, it turns out there were mechanical resonances. So basically, we were trying to ramp up the speed every once in a while. In the process of ramping to its full speed, a resonance would happen, and the motor would simply drop out of rotation just suddenly. It would spin, and it would just then suddenly halt hard. Um, and so we had to figure out where are the mechanical resonances. And make sure that in the ramp circuit, well, in the ramp firmware, not circuit, like in the program, in the ramping program, that we basically jumped over these mechanical resonances to achieve the desired speed. In order to achieve the desired speed, we could not run the stepper motor at the intended at its intended speed. Or at its intended voltage, I should say, that's point. We couldn't run the stepper motor at its intended voltage. We had to go a much higher voltage in order to force current in and out of the coils in a faster fashion. We needed to charge and discharge the coils at the stepper motor faster than it was designed for. The problem now is, so basically we're operating a 5-volt stepper motor at 24 volts. So we had to make sure that it didn't burn out. So we had to use a current control, basically a chopper mechanism that would examine the rise of current in the stepper motor and would basically chop when it exceeded the set point, when it exceeded the set current that we wanted. So, and that is not unusual. Like that is actually not an unusual technology to use for a stepper motor. It is just like one thing that we thought was a simple problem. Okay, we just grab a random stepper motor, and it turned into this long experimenting, as in how can we do this? And it worked in the end. Is that the kind of unusual load that you meant, or do you want like other examples?
No. Thank you. It's very interesting example, and I have one more question, maybe partly related. It is about maximum power.
Mhm.
Uh, so maybe you have a real example in your practice, of course, regarding maximum power control. using a microcontroller. What were real values approximately of maximum power?
Of maximum power, in my current line of work, which is photovoltaic, which is basically solar. It has to do with solar installations, um, but it's all for low voltages. It's all for 12 and 24 volts. So there is a lot of, there are very high currents that we're dealing with. Measuring, I have at the moment worked with circuitry and design circuitry to measure up to 500 amps in a shunt resistor. But we are not typically driving that much power. The typical currents that we are driving is more in the range of 40 amps to maybe 100 amps. It is like partially solar controllers. The main design is being outsourced in the current company, but we still have to test and we have to design like some test circuitry. So yeah, those are the power ratings. If it comes to measuring currents, um, up to 500 amps, which is kind of difficult. Like I don't have a shunt resistor here, but the shunt resistor is like a solid piece of copper, basically, and um, it's a pretty heavy device. Like normally, in other situations, I would go to magnetically, I would go to a different type of current measurement. But the problem is like the type that measures the magnetic field that is around the conductor. The problem is that a shunt resistor is cheap. So this is for consumer devices. And so we can get a shunt resistor that is rated for 500 amps for $7, $8 or so. And it's hard to compete with that cheapness, like using other technologies. So yeah, that is what is being used at the moment. Otherwise, I've worked on circuitry that was using, again, the highest I've looked at MOSFETs, the highest was maybe 140. There was, I think, an IRF 7443. Let me check. I'm just bringing that up. IRF 43, if I'm not completely. No, that's no, that's not it. It was a MOSFET, an N-channel MOSFET. It was in the range of like 140 amps or so.
Okay, thank you. I have no question. Maybe other participants have questions? No more questions. So thank you again, Mr. Rademacher. It was really, really interesting.
Thank you so much for the opportunity.
We have message in chat. Thank you very much for the interesting speech, for the interesting lecture. Okay, thank you.
Okay, thank you.